Thanks. Thanks for having me giving me the opportunity to talk about my research. I'm going to talk about actually existing data, which give constraint on the feedback physics in cosmological simulations. And the data set I'm focusing on is the ERAS, which is the Euro-Zeta All-Sky Survey, as you all know. It's just a brief recap. It's a German-Russian mission, and it completed 4 full sky scans before the war broke out, which stopped the mission. And it averaged on a few hundred seconds per exposure. And the first Western galactic sky has been released from the German side. And the observation data that I'm going to compare with simulation is from the ERAS-4, which means it's a 4 full sky scan from this paper, Zhang et al. So they used the SDSS main galaxy sample to do the stacking of the Euro-Zeta CGM. And they divided the sample into 3 stellar mass bins, a Milky Way mass-like stellar mass bin, an M31 stellar mass bin, and a 2 times M31-like stellar mass bin, basically in order of increasing in order of increasing stellar mass. So here's just a table showing the average stellar mass, the redshifts, and the number of galaxies that they stack is around between 20 to 30,000 galaxies. And they modeled out point sources from AGN, X-ray binary, and satellite galaxies. And what they left is this this purple shaded regions and purple lines, which they referred to the X-ray emission of the CGM. And they also tried to fit a beta model to it. And so this is the purple lines are what we are going to compare with the simulations. And the simulations that we are exploring is from the CAMELS simulation. So CAMELS stands for Cosmology and Astrophysics with Machine Learning Simulations. What we are focusing on is three simulation suites from the CAMELS, the Illustrious TNG suite, the SIMBA suite, and the Astrid suite. All comes with different feedback physics. And for each suite, they vary 4 different feedback parameters, 2 in the select feedback and 2 in the AGN. So here it's just a description of the feedback. So supernova 1 stands for the supernova energy per output per star formation rate. That's for the TNG and Astrid 1, and it stands for the mass loading factor for the SIMBA. And SN2 is the wind speed of the supernova. And AGN1 for Illustrious TNG and Astrid is the kinetic energy feedback. And for SIMBA, as you all know, it's a jet feedback, so it characterizes the momentum flux of the AGN jet. And AGN2 is, for TNG, is so-called the burstiness of the AGN, or the ejection speed of the AGN wind. SIMBA, it refers to the jet speed, and for Astrid, it refers to the thermal AGN feedback. So we use 1,000 simulations for each of these fronts, which sample the parameter space of these 4 parameters using a Legend hypercube parameterization. We focus on using a 25 megaparsec box, which have run all the way to redshift 0. And it has a resolution of 10 to 7 solar masses with OK resolution at around 2 kiloparsecs. So here's the comparison of our X-ray surface brightness profile with those from the ERAS results. So the color lines indicate the strength of the feedback, and we're showing the SN1 parameter for the Illustrious TNG. So redder color indicates a stronger feedback effect. So if you increase the feedback, it basically crunches more star formation, so it retains more hot gas. So it increases the X-ray surface brightness across all the 3 mass bins. And you can see that also the spread in the, as we vary the strength of the supernova feedback, there's more spread here in the lower mass bin, basically just reflecting the fact that the lower mass bin and the weaker mass bin, they're more sensitive to AGN feedback due to the shallower potential. And here we are comparing to the observations in black points. In the Milky Way mass bins, the fiducial model, meaning that all the parameters are set to 1, it it fits the observations pretty well. But generally, the ERAS result is under, or other way, the illustrious TNG fiducial model, they kind of overpredicts the M31 and 2 times M31 mass spin in terms of X-ray surface brightness. And going on to the wind speed, the story is similar. If you increase the wind speed, it reduces star formation, leading to higher gas fraction and therefore higher X-ray surface brightness. And again, we see that the Milky Way mass spins, they're more sensitive to the feedback strength. Here, it's more sensitive to the wind speed of the supernova. And here, I'm just showing the AGN feedback, the feedback energy, and the burstiness, again, for the illustrious TNG. In this case, in almost all 3 bins, they are not very sensitive to AGN feedback. There's some variation in the, when we vary the burstiness, there's some variation in the X-ray surface brightness, but they are all very small. So instead of looking at the X-ray surface brightness, we can also look at the X-ray luminosity style mass relation. And this is basically we integrate over the X-ray surface brightness up to R500 and measure the X-ray luminosity, and we compare that with the ERAS result. We see the same story here, that the X-ray luminosity cell mass relation, they are more sensitive to the supernova feedback, both the supernova feedback energy and the wind speed, and they're not very sensitive to the AGN feedback at all. Yeah, I'm just going to gloss over the other 2 runs, which show similar story, that when we compare the X-ray luminosity cell mass gain relations for SIMBA, the SIMBA runs, they're more sensitive to the supernova feedback, both in terms of wind speed and also the SN1, which is the mass loading. And again, the AGN feedback, the jet feedback is not very effective at all in changing the X-ray luminosity mass relation. And in general, SIMBA underpredicts the X-ray luminosity M-star relation, which is consistent with previous works as well. And Astrid, it's a bit interesting, as it generally overpredicts the X-ray luminosity for the halos that we study. And it exhibits a very strong dependence on both the supernova energy and also the wind speed. And for the AGN2 here, for Astrid, which represent the thermal energy feedback, we also see a sort of non-monotonic behavior, such that if we increase the AGN feedback to very high value, it actually decreases the X-ray luminosity. And we suspect that it's because the strong thermal AGN feedback that actually puffs up the gas density too much, so it reduces the X-ray luminosity if we go to too strong AGN thermal feedback. And with the data and with a model, we can actually put constraints on these feedback parameters. So what I did is I just ran an MCMC analysis, and these are the sort of the best fit parameters preferred by the ERAS data. And so ERAS, the ERAS data prefer a higher supernova energy and AGN kinetic feedback energy and burstiness for the illustrious TNG compared to the fiducial TNG values, which is value of unity. So you can see that all the parameters here, except for this one, it prefers a higher value than 1, which means that the ERAS result prefers a stronger feedback in all, except for this supernova 2, which is the wind speed.
2 minutes.
Okay. And we here, so basically, we repeat the same similar analysis for both the SIMBA and Astrid runs. You can see that for SIMBA, we almost always prefer a higher value of feedback. And for Astrid, we prefer high value of supernova energy, a higher value of AGN1 energy, but AGN kinetic energy, but lower values of the other 2 parameters. So this is a short talk, and this is my conclusion. And with the CAMELS simulation suite with varying feedback, we're able to forward model X-ray dependence on the feedback physics at the CGM scale. And combining with the ERAS data, we're able to put constraints on these feedback parameters in 3 modern cosmological summations, TNG, SIMBA, and Astrid. So I'll take questions, and thanks.
Oh, yeah.
Just a kind of a quick question of what like radius does the observational data go out to within galaxies? But I think you showed it at the beginning, but I think in this case.
Yeah, so the dot dash line is the virial radius.
Okay.
Yeah.
And the simulation data within the virial radius?
In the simulations, I go all the way out to 3 times the virial radius.
Okay.
But when I do the comparison and fitting, I only compare up to the virial radius.
Right.
How about CAMELS? ERAS data, how far do you go?
So it's a stacking measurement, right?
Yeah.
So how far they go in terms of the physical radius depends on the redshift bins that they are stacking with.
When you compare with the observation, the CAMELS data and your simulation data in terms of LX versus M star, for example.
Oh, so for the LX M star, for the scaling relations, we compare up to alpha venture.
Yeah, I was wondering because those ERAS derived like luminosities from the stacks are thousands of galaxies that are accounting for those values, right? Like, are you just comparing it to single halos, like in the simulations, or are you also doing a stacking? And so
I'm also doing a stacking in the simulation.
Okay.
So what we did actually in the simulations, so we have 1,000 boxes, and each box is 25 nanoparsecs. It has its own number of galaxy halos, and so we measure the average X-ray surface brightness profile and X-ray luminosity for the stellar mass, which is batching the stellar mass of the observations. So we do the similar stacking procedure for that.
Any more questions?
Maybe a comment and a question.
Yeah.
So the comment is several times you said that, say, the AGN-related parameters do less than the supernova feedback-related parameters, right? But I think because of the small volumes, it's not really true. Right? In a large volume where you have larger halos more represented, the AGN feedback parameters would look more important. My question is about the MCMC. So very cool, but there's other observational constraints on the galaxy population. So if you added in something totally orthogonal, like the stellar mass function, would you still favor changing the parameters as you suggest, or not? Right? More broadly, how do we incorporate, not just X-ray, but beyond?
Yeah, I think that's a good question. So something that we'll consider adding in analysis. We do look at the M star halo mass relation, but we haven't looked at the stellar mass function, which I know that it's the stellar mass function is used to do the calibration of the simulations.
Maybe one more question? Yeah.
Right, so, you show a lot of plots with a lot of lines on there where the different simulations are distinguished by different underlying physical treatments of AGN and star formation feedback. And from where I'm viewing this talk, I don't know the underlying physics or how each of these things was parameterized. So I'm wondering whether it's possible in this form of analysis to correlate the outcomes not with the labels for different simulations, but like with the total energy input from AGN, something that's physically measured about the simulation. Total energy input or mass input to the CGM, so that these abstract parameterizations kind of drop out and we're looking at physics versus physics.
Yeah, I think that's a good suggestion. And in some way, these are physical. They do have physical meanings. So, although I agree, it's not very obvious. Yeah.
Okay, that's our thanks. Speaker again.